Now, it's obvious to everybody that the phenomena of the world are evidently irreversible. By that I mean things happen that don't happen the other way. You drop a cup and it breaks, and you can sit there a long time waiting for the pieces to come together to come back into your hand. If you watch the waves breaking at the sea, you stand there and wait for the great moment when the foam collects together, rises up out of the sea, and falls back further out from the shore. Would be very pretty. As a matter of fact, the demonstration of this in such lectures is usually made by having a section of moving picture in which you take a number of phenomena and running the thing backwards and then see all the laughter. The laughter just means this ain't going to happen in the real world. But actually, that's a kind of a weak way to put something which is so obvious and deep as the difference between the past and the future. Because even without an experiment, our very experiences inside are completely different for past and future. We remember the past, we don't remember the future. We have a different kind of awareness about what might happen than we have of what most likely has happened. The past and future look completely different psychologically and so forth. And the questions of memory, of apparent freedom of will, in the sense that we feel that we can do something to affect the future, but none of us, or very few of us, believe that there's anything you can do to affect the past. And remorse and regret and hope and so forth are all words which distinguish perfectly obviously the past and the future. Now, if the world of nature is made of atoms, and we too are made of atoms that obey physical laws, there's obvious distinction between what happened, the past and the future, and this obvious irreversibility of all phenomena, you would think would most likely have obviously its interpretation in that some laws, some of the motion laws of the atoms are going one way, that the atom laws are not such that they can go either way, that there's somewhere in the works some kind of a principle that wuxels only make wuxels and never vice versa, and so the world is turning from wuxely character to wuxely character all the time. And that this one-way business of the interactions of things is the thing that makes the whole phenomena of the world seem to go one way. And yet we haven't found it yet. That is, in all the laws of physics that we've found so far, there doesn't seem to be any distinction of the past and the future. That the moving picture should work the same way going both ways, and the physicist who looks at it should not laugh. Details now to be explained. Let us take the law of gravitation as our standard example. If I have a sun and a planet that I started off in some direction going around to here, and then take a moving picture of this, say it gets to here. Now take a moving picture of this backwards. Take a moving picture of it, excuse me, and run the movie backwards and look at it. What happens? Planet goes around the sun in an ellipse. The speed of this way, of course. Starts here, goes to here, keeps on going around. Goes in an ellipse. The speed of the planet is such that the area swept out by the radius is always the same in equal time. Just does exactly the way it ought to do. It's perfectly satisfactory. It cannot be distinguished from the one going the other way. So the law of gravitation is of such a kind that it doesn't make any difference. If you show the phenomenon running, any phenomenon involving just gravitation running backwards on a film, it'll look perfectly satisfactory. Put it precisely more this way. If at a given instant the particle moving this way, if all the particles in a more complicated situation would have every one of their speeds reversed suddenly, then the thing will just unwind through all the things that it wound up into. That is, if you have a lot of particles doing this, then you suddenly reverse the speeds, they will completely undo what they did before. Now this is in the laws of gravitation, which say that the velocity changes as a result of the forces and so on. If I reverse the time, the forces are not changed, and so the changes in velocity are not altered at corresponding distances. And so each velocity then has its succession of alterations made in exactly the reverse way that they were made when it went out before, and it's easy to prove that the law of gravitation is time reversible. The law of electricity and magnetism, time reversible. The laws of nuclear interaction, time reversible as far as we can tell. The laws of beta decay that we talked about at a previous time, also time reversible. The difficulty of the experiments of a few months ago, which indicate that there's something the matter with some unknown about the law, suggests the possibility that in fact it may not be also time reversible, but we shall see. But at least the following is true. This beta decay that we're talking about, which may not be time reversible, but I don't know, is a very important phenomenon for most ordinary circumstances. The possibility of my talking to you does not depend on that happening. It does depend on chemical interactions. It depends on electrical forces. It doesn't actually depend much on nuclear forces at the moment, but it depends also on gravitation. But I am one-sided. I speak and the voice goes out into the air and doesn't come sucking back into my mouth when I open it. And this irreversibility cannot be hung on the phenomena of beta decay. In other words, we believe that there are in the world most of the ordinary phenomena which are produced by atomic motions which are according to laws which can be completely reversed. So we have to look some more to find the explanation. If we look at this more carefully and a planet's moving around the sun more carefully, you soon find that it isn't quite right. For example, the Earth's rotation on its axis is slightly slowing down. That's due to tidal friction. And you see that friction is something which is obviously irreversible. If I took a heavy weight on the floor here and pushed it, it would slide and stop. If I stand and wait for it, it doesn't suddenly start up and speed up and come into my hand. So a frictional effect seems to be irreversible. But a frictional effect, as we discussed at another time, is the result of enormous complexity of the interactions of the block with the wood, the jiggling of the atoms inside, that the organized motion of the wood, of the block, is changed into disorganized, irregular wiggle-waggles of the atoms in the wood. So that therefore we should look at the thing more closely. As a matter of fact, we have here the clue to the apparent irreversibility. I take a simple example of, for example, if we have blue water, say ink, and white water, that's water without ink, in a tank with a little separation, and pull out the separation very delicately, then it starts separate blue on one side, white on the other side. Wait a while. Gradually the blue mixes up with the white, and after a while the water is blue. I mean, it's sort of 50-50, a color uniformly distributed throughout. Now if we wait for a long time and watch this for a long time, it does not by itself separate. Or you can do something. You can get the blue separated again. You can evaporate the water and condense it somewhere else and collect the blue dye and dissolve it in half the water and put back this thing and so on. While you're doing all that, however, you yourself are causing irreversible phenomena somewhere else. So by itself, it doesn't go the other way. And that gives us some clue. Let's look at the molecules. Suppose that we took a moving picture of the water, of the blue and the white water mixing. It would look funny if we ran it backwards, because we'd start with uniform water and gradually the thing would separate and would be obviously nutty. Now we magnify the picture so that every physicist can watch atom by atom to find out what happened irreversibly, where the laws of balance of forward and backward broke down. And so you start and you look at the picture and you have blue atoms. That's ridiculous, but we'll call it that. We have atoms of one kind and atoms of another kind jiggling all the time in thermal motion, wiggling and bouncing. And if we were to start at the beginning, we would have mostly atoms of one kind on one side and atoms on the other kind on the other side. Now these atoms are jiggling around. It's too small a box. You need more to get this effect. Billions and billions of these atoms. Now these atoms are jiggling around. I just put one more, but I'm getting tired of making it. Now these atoms are jiggling around. And if we start all on one side and all on the other, we see, of course, that in their perpetual irregular motions, they'll get mixed up. And that's why it gets to be more or less uniformly blue. But let's watch any one collision. Here's a particular collision selected from that picture. Here's this molecule moving this way and this one moving this way. And they come together, say, in the moving picture, and they bounce off this way. Now you run that section of the film backwards, and you find a pair of molecules moving this way, bouncing off that way. And the physicist looks with his keen eye and measures everything and says, that's all right, that's according to the laws of physics. If two molecules came this way, they would bounce that way, and if they came that way, they would bounce this way. It's reversible according... The laws of molecular collision are reversible. So if you watch too carefully, you can't understand it at all. Because every one of the collisions is absolutely reversible, and yet the whole moving picture shows something absurd, which is that the molecules start in the reverse picture. The molecules start in this condition, blue, white, and blue, white, and so on, all mixed up. And as time goes on, through all the collisions, the blues separate from the whites. And they can't do that. But that's not natural, that the accidents of life will be such that the blues will separate themselves from the whites. Yet, if you watch this reverse movie very carefully, every collision is okay. Well, you see that all there is to it, that the irreversibility is caused by the general accidents of life. That if you start with a thing that's separated like this and just make irregular changes, it gets more uniform. But if you start with something that's uniform and make irregular changes, it doesn't get separated. It could get separated. It's not against the laws of physics that these things bounce around so that they separate. It's just unlikely. It never happened in a million years. And that's the answer. The things are irreversible only in the sense that going one way is likely to go, but going the other way, although is possible and is according to the laws of physics, wouldn't happen in a million years. It's just ridiculous to expect that if you sit there long enough, the jiggling of the atoms will separate a uniform mixture of ink and water into ink on one side and water on the other. Now, if I had put a box around here so that this was all the molecules that there were, as time went on, they would get mixed up. But if you're patient, I think you could believe that in the perpetual irregular collisions of these molecules, after some time, not necessarily a million years, maybe only a year, when you keep watching, accidentally they get back more or less like this. In the sense, at least, they get back far enough to say that if I drew a line through all the whites on one side and all the blues on the other, it's not impossible. However, the actual objects with which we work have not only 4 or 5 blues and whites, but they have 4 or 5 million atoms. And it's just not likely that 4 or 5 million are all going to get separated like this. And so the apparent irreversibility of nature does not come from the irreversibility of the fundamental physical laws. It comes from the characteristic that if we start with an ordered system and have the irregularities of nature bouncing, then the thing goes one way. Therefore, the next question is, how did it get ordered in the first place? That is to say, why is it possible to start with the ordered? You see, the difficulty is that we start with an ordered thing, we don't end with an ordered thing. One of the rules of the world is that the conditions at the beginning, that the thing goes from an ordered condition to a disorder. Incidentally, this word order and disorder is another one of those terms of physics which aren't exactly the same as it is in ordinary life. The order need not be interesting to you, human beings. It's just a question that there's a definite situation. They're all on one side and all on the other, or they're mixed up. And that's the order to disorder. Maybe you like it better mixed up, but that's not more ordered anyhow. Now, the question is then, how does the thing in the first place get ordered? And why, when we look at any ordinary situation which is only partly ordered, we can conclude that it probably came from more ordered. If I look at a tank of water in which it's very dark blue on this side and very clear white water here and sort of bluish water in between, and I know that that thing has been left alone for 20, 30 minutes, then I will guess that it got this way because it was bluer before. For instance, if I find, that the separation was more complete in the past. If I find, for example, two objects, this is a good example as any. If I wait longer, then the blue and white would get more intermixed. And if I know that this thing has been left alone for a sufficiently long time, I can conclude something about the past condition. The fact that it's smooth in here could only arise because it was much better in the past, much more satisfactorily separated. Because if it weren't more satisfactorily separated in the past, in the time since then, it would have gotten more mixed up than it is. So, it is therefore possible to tell from the present something about the past. Although physicists are really not do this much, physicists usually like to think that all you have to do is say, these are the conditions and what happens next. But all our sister sciences have a completely different problem. In fact, all the other things that are studied, history, geology, and astronomical history, all have a problem of this kind. I find they're able to make predictions of a completely different type than a physicist. A physicist says, in this condition, I'll tell you what will happen next. But a geologist will say something like this: I have dug in the ground and I found certain kinds of bones. I predict that if you dig in the ground, you'll find a similar kind of bone. The historian, although he talks about the past, can do it by talking about the future. When he says Napoleon exists, or Napoleon was, or that the French Revolution was in 1783, he means that if you look in another book about the French Revolution, you'll find the same date. 1789, maybe. That's pretty accurate for a physicist to have the third decimal figure. The three figures. Now, the thing that he says is that he makes a kind of prediction about something he has never looked at before. Documents that have still to be found. He predicts that the documents, if there's something written about Napoleon, will coincide with what is written in the other document. And the question is how that's possible. And the only way that that's possible is to suggest that the past of the world was more organized in this sense than the present. Some people have proposed at one time, the physicists only have proposed this, some physicists, that the way it got ordered was this: that the whole universe is just irregular motions like this. And then if you wait long enough with 5 atoms, of course it can get separated accidentally. And all that has happened is that in the world has been going on and going on and going on and going on and going on, and it fluctuated. That's what this is called. When it gets a little bit out of ordinary, it fluctuated, and now we're watching the fluctuation undo itself again. How do we know that isn't the case? You say, well, how long you would have to wait? I know, but if it didn't fluctuate far enough to be able to produce evolution, to be able to produce an intelligent person, we wouldn't have noticed it. So we had to keep waiting until we were alive to notice it. So we have to have at least that big a fluctuation. But this is incorrect, I believe. I think that's a ridiculous theory for the following reason. That if the world were much bigger, and there were atoms all over the place, and they started from a completely mixed up condition, all over, and I happen only to look at the atoms here, and I find that the atoms here are separated, I have no way to conclude that the atoms anywhere else are separated. In fact, if the thing were a fluctuation and I noticed something odd, the most likely way that it got there is that there's nothing odd anywhere else. That is, I have to borrow odds, so to speak, to get this thing lopsided. And there's no use on borrowing too much. It's much more likely, of all the possible ways in which these 6 atoms can be on one side and these 7 on the other side, of all of the possibilities, the most likely condition of the rest of the world is mixed up. And therefore, an astronomer, looking at a star that he's never, although when we look at the stars and we look at the world, we see it's ordered, and it could be a fluctuation. The prediction would be that if we look at a place that we haven't looked at before, it'll be disordered and a mess. That the separation of the matter into stars which are hot and space which is cold, which we've seen, although if you say it could be a fluctuation, then in places that we haven't looked, we would expect that the stars are not separated from the space. And since every time we make a prediction that in a place that we haven't looked, we'll see the same statement about Napoleon, or we'll see stars in a similar condition, or that we'll see bones like the bones that we've seen before, the success of all those sciences indicate that the world did not come from a fluctuation, but came from a condition which was more separated, more organized in the past than at the present time. And therefore, I think it's necessary that to add to the physical laws the hypothesis that in the past the universe was more ordered in the technical sense, less mixed up, than it is today. And that this statement is the added statement that's needed to make sense and to make an understanding of the irreversibility. That statement, of course, is itself lopsided in time. It says something about the past is different than the future. But it comes outside of the province of what we ordinarily call physical laws, because we try today to distinguish, maybe someday we won't do that, but we do today distinguish between the laws which tell how something moves if you start it in a certain way, and those statements about how the universe got the way it gets, or has been, what it was in the past, and what it's going to get to be. No, excuse me. The statement of the physical laws which govern the rules by which the universe develops, and the law which states the condition that the world was in the past. That's considered to be astronomical history. Perhaps someday that will also be a part of physical law. Now, there are a number of interesting features of irreversibility that I think I would like to illustrate. One of them is to see how exactly an irreversible machine really works. Suppose that we build something that we know ought to work only one way. And what I'm going to build is a wheel with a ratchet on it. A ratchet means just this, that we have a notched wheel with steps. So,